today we're going to be talking about telescopic sums again. In this video, we're going to be discussing these three examples. First of all, let me remind you a little bit about telescopic sums. In this, an is equal to fn plus 1 minus fn. We'll go in more detail about what that means right now. First of all, in our first example, we have it so that we have 4k divided by 4k to the fourth power plus 1, where k is equal to 1 all the way to n. So first of all, we're going to use this factoring trick where where we replace k was a and b and 1 was b. So we have 4a to the fourth power plus b to the fourth power. So we can also write this as 2a squared plus b squared minus 2ab squared. So by using the trick that we know as a squared minus b squared is equal to a plus b times a minus b, we get 2a squared plus 2ab plus b squared times 2a squared minus 2ab plus b squared. Now, if we put this into our denominator over here, then we get that this is equal to 4k divided by 2k squared plus 1 squared minus 2k squared, but we can also write it as this over here. Now, first of all, First of all, how do we do this? Well, first of all, let's separate this into two separate fractions. So this is just equal. In this next problem, we have it so that we have to find the sum of k divided by k plus 1 factorial, where k is equal to 1, all the way to n. Here we're going to use two things. First of all, k is equal to k plus 1 minus 1. This seems pretty obvious, but we're going to have to use this in the problem, and it's really important. Also, we have k plus 1 factorial is equal to k plus 1 times k factorial. This also seems pretty obvious, but they're both important in this problem. So let's put those values in. This means that this is equal to k plus 1 minus 1 divided by k plus 1 times k factorial. So let's divide this into two fractions, shall we? K plus 1 as a numerator for one of them, and minus 1 as a numerator for the other one. So this is also the same thing as 1 divided by k factorial minus 1 divided by k plus 1 factorial. So if we let fk equal to 1 divided by k factorial, then we can cancel a bunch of stuff because, well, we don't have to do the same thing in this problem where we had to prove that this is equal to this because, well, fk plus 1 is already equal to this over here, so you don't have to worry about that in this problem at least. So if we put it in, a bunch of it cancels and we get that this is equal to f1 minus fk plus 1. So put those values in. This is equal to 1 minus 1 divided by k plus 1 factorial. And there you go. That's our answer to our second example. Next, we have it so that we have to find the sum of this over here. We have to find the sum of this over here where k is equal to 1 all the way to n. So first of all, k squared plus k plus 1 is equal to k plus 1 squared minus k. So if we put that in, we get that this over here is also equal to k plus 1 squared times k factorial minus k times k factorial. However, what we can do here is that we can move one of these k plus 1 squares, because there are two of them, and multiply by this over here. So we get k plus 1 times k plus 1 factorial minus k times k factorial. So if we let fk equal to k times k factorial, since we don't have to change it because, well, these two are the same anyway, we're going to end up with this sum being equal to fk plus 1 minus f1. And so if we put it in, we get that this is equal to k plus 1 times k plus 1 factorial minus 1. And there you go. That's our answer to our third and last example of this video.